Professor Peldon. This is Algebra 2, Chapter 5, Section 6. This is Part 2, which is the nonlinear inverses. In Part 1, we did linear inverses, which is the lines, and they always had inverse functions. When you are nonlinear, you don't always have an inverse function. In the polynomials, you have even and odd functions. Down here we'll do examples of a squared and a cube, which one is even, one is odd. And they might not have an inverse function over their entire domain. Therefore, we have to restrict the domain to make that actually happen. Okay, so let's try these as an example. Alright, so the original for this one is y equals, let's change colors here. Y equals x squared, that is the original. So if we do a table of values, x and y, for the original, plug in some standard values. So if I square 2, I get 4. Square 1, I get 1. Square 0, I get 0. So we get a standard parabola. You've been graphing for years now. Probably at this point you don't need to plug in numbers for yourself to make a graph, but for the sake of this, we're going to make it a little bit easier to understand inverse. So if I switch the values to make the inverse, you get x squared equals y. Sorry, we did that wrong. We get x equals y squared. I'm sorry. So we square root x and square root y squared. But remember, an even root has to have a plus or minus. So essentially, y equals plus or minus the square root of x would be the supposed inverse. So let's try the table for this. Well, if it's an even root, I can't do negatives, so I can only do positives. What are some easy ones I can do? Well, 0, 1, and 4 are square rootable. Alright, square root of 0, square root of 1, square root of 4. You can do other than like 2 and 3 if you want, although 2 and 3 give you decimals. I don't really want to graph decimals. Maybe you do. If you do, that's fine. That's up to you. I choose not to graph the decimals myself. Okay, so at 0 at 0. At 1, I'm at positive 1 and negative 1, and 1, 2, 3, 4. I'm at positive 2 and at negative 2. Okay, so you're like, oh, well, looks like an inverse, but it's really not, because it doesn't pass the vertical line test. Okay? And however, the values are switched. If you graph the y equals x line, the values from y to x are switched. Thus, they are inverses. But the problem is, if it's not an inverse function, because if you look closely, this is not a singular function. This is 2. This is the positive square root of x. This is the negative square root of x. So there is no singular inverse function for this. So there is no inverse function that exists. In order to make one exist, I would have to limit the domain, basically. I would have to get rid of 2 parts of it to actually exist. So unto itself, there is no inverse that exists for the even polynomial of x squared. So if we do the cubic, y equals x cubed, that's my original. Again, you don't necessarily need to do a table, but we're going to for the sake of this. Okay, so we'll plug in some basic values, negative 2, negative 1, 0, 1, and 2. So if I cube each of those, I get negative 8, negative 1, 0, 1, and 8. So at negative 2, I'm at negative 8, negative 1, 0, 0, 1, 1, and 2, 8. So that gives us our standard cubic function. Okay, so we'll do the inverse now. So the inverse is x equals y cubed. Therefore, I have to do the cube root to both sides. Don't have to do plus or minus since it's an odd root. So cancels, cancels. Y equals the cube root of x. So we do the inverse table now. Right, that's the inverse. That is the, whoops. original. I can cube root anything I want, positive or negative, because you can do odd roots of negatives. So I'll do -8, -1, 0, 1, and 8. Cube root of -8 is -2, right? And so on and so forth. I get -1, 0, 1, and 2. So if I graph those, at -8 I'm at -2, -1, 1, 0, 0, 1, 1, and 8, 2. So we get our, whoops, a little off on the curves there, but that's okay. Okay, what you should notice is the tables flipped, because we're flipping the x and y values. The tables flipped. We flipped the x and y tables. However, here, this one, no matter where I go, passes the vertical line test. Okay, and all the values for the original and the inverse lie along the line y equals x. So they just flopped their x and y values. So an inverse function does exist for all domain when it comes to the odd polynomial function. So essentially what we can say is f -1 of x equals the cube root of x. Okay, so this one actually does have an inverse for the entire domain. We don't need to restrict it. Okay, let's do some examples. Okay, so in the first example, 2x cubed plus 1, for what domain does it actually have an inverse? Okay, so this is my original. Go to blue. So domain and range. Okay, so it's a cube function. I can cube anything I want, positive, negative, or infinity. So there is no restriction here. Okay, and y equals 2 times something cubed plus 1. If I plug in negative infinity, I'm going to get 2 times negative infinity, because 3 negatives is a negative, plus 1. So essentially I get negative infinity after I multiply it by 2 and add 1. And if I do positive infinity, I get positive infinity. So the output is not going to change either. And you can see clearly from the graph on the right, it goes forever up, forever down, forever left, forever right. Okay? So input, output, domain, range. So the original has no restrictions. Okay, we'll do the inverse now. So inverse, you need to switch the variable. So x equals 2y cubed plus 1. Alright, add subtract step. We'll subtract 1. X minus 1 equals 2y cubed. Multiply, divide. We'll divide by 2. So x minus 1 over 2 equals y cubed. Exponent radical, so we'll cube root. So the cube root of y cubed equals the cube root of x minus 1 over 2. So cancels. Y equals the cube root of x minus 1 over 2. Although that is not written properly. I see a lot of you guys do that also. That is incorrect, because the whole thing is cube rooted, right? Not just the top. So we want to know, is it the inverse of the entire domain? Well, remember a little trick. Domain. The range of this is the domain of the final, right? So negative infinity to infinity. Okay? Because the range of the original is the domain of the function, because they switch. Okay? And you can prove that to yourself. You can do an XY table to graph it. So what are some things that will work here? So if I plug in 1, I'll get 0 over 2, which is 0. So 1, I'm at 0. Let's see what else numbers that'll work nicely here. If I plug in negative 1, I'll get a negative 2 on the top. Divided by 2 is negative 1, so that gives me negative 1. And if I plug in 3, I'll get 3 minus 1 is 2 over 2 is 1. So I get a nice cubic function this way. My art skills are not very good there. But either way, they fall along the y equals x line. Okay? Remember, if you plug in the domain into it too, you'll get the range. So if I plugged in the negative infinity to infinity, which you don't need to do, you'll get negative infinity over 2, which is negative infinity, which is negative infinity. And if you put the positive infinity in there, nothing really changes. So the range here would be negative infinity to infinity, which you don't need to put, and only ask for the domain, because again, they switch. The domain of the original is the range of the inverse, so vice versa. But you don't need any of that green part I wrote there. We can look at a calculator to verify also what we're saying too. So the original one was 2x to the third plus 1. And the inverse menu, graph entry, function was the third root. Oop, didn't click in the box by accident there. And then the fraction was x minus 1 over 2. Ooh. X minus 1 over 2. Okay. It's a little less sloppy in my hand graph there, and you can see clearly, whoops. This folds nicely on the y equals x line. So it's an inverse for the entire domain, basically. Okay. Next problem. So in this case, this is the original. So the last one was an odd function. This one seems to be an even root. So domain and range. So this cannot be everything because it's an even root. If you have denominators or even roots, you have restrictions. So don't think about what you can be, think what you can't be. X minus 3 has to be greater than or equal to 0. You can't take even roots of negative numbers. So we have x must be greater than or equal to 3. So this is 3 to infinity. I can't get to infinity, but I can get to 3. So that's input, output, range. So plug it in. 2 times the square root of 3 minus 3, and 2 times the square root of infinity minus 3. Well, that's going to be 2 times 0, and that's going to be 2 times infinity. So that's 0 to infinity. So my range is 0 to infinity. Okay, and if you look at the graph, that verifies over there. It starts at 3, goes forever to the right. Starts at 0, goes in forever up. Okay. All right, let's do our inverse now. Inverse. Okay. So we need to switch the variable. So x equals 2 square roots of y minus 3. Add subtract step. There isn't one in this case because the add subtract is in the parentheses. Multiply divide. We'll divide by 2. So x over 2 equals square root of y minus 3. Exponent radical. So we'll square this side. Oops, not a y, it's an x. That's my mistake. So these will be x squared over 4 equals y minus 3. Grouping symbol step, we'll add 3. So x squared over 4 plus 3 equals y. Okay, so now the question is for f negative 1 of x, we need to specify the domain. So here's where it's tricky, you got to pay attention. Because you can square any number you'd like. I can square positives, I can square negatives, I can square 0. So typically your domain would be negative infinity to infinity. However, the range of the original is the domain of the inverse, so this must be 0 to infinity. Okay, well if I plug in 0, I get 0 over 4 plus 3, which is 0. 3, excuse me. If I plug in, let's see, 2, that's 2 squared over 4 is 4, plus 3 is 4. So again, if I put in 2, I'm at 4. If I plug in 4, that's what? 4 squared is 16, divided by 4 is 4, plus 3 is 7. So if I go to 4, I'm at 7. So it goes like this. But I can plug in negative numbers here, because I can square negative numbers. But the problem is, if I plugged in negative numbers, it would give me things out here. And I don't want that, because this needs to be symmetrical on this line. Okay? So, this has a restricted domain as a result. And we'll see the graph. We'll look at the graph and calculator, verify. So we go to the graph and calculator, make a new graph. The original was 2 times the square root of x minus 3. Okay, square root function. Menu, graph entry, function. And the inverse that we found was x squared plus 3. And we get this, which clearly is not the inverse of that. So we need to restrict the inverse that we found. So this cannot exist, so therefore the domain must be from 0 to infinity. We cannot put in the negative part, because we need this to be symmetrical on the y equals x. Okay? And this was 3 to infinity for the original. Okay? Alright, pause the video, try these student problems. Alright, student problems. So this is the original. So domain and range. So squaring, it's a parabola. You can square any number you want, positive, negative, or infinity. So typically you would think negative infinity to infinity. So if I plug that in, all right, try it for yourself. Well, we'll do y equals negative 1 times something squared plus 1. Okay? Remember, there's a negative. I like to put the negative 1 there. So if I plug in negative infinity, I get order of operations, which is exponents first. So if I square a negative, I get a positive. Then I multiply, so I get negative infinity plus 1. So the final is just negative infinity. If I change this to a positive infinity, nothing changes, because if you square a positive, you still get a positive. So no matter what I do, I'm going to get negative infinity. So the question is, if I can't get a positive number, what's my highest number? Well, you think to yourself, what do you plug in to get 0? Because that's the last number before you reach positive, correct? Since I can't get a positive number, what am I plugging in here? Well, if I plug in 1, if I square 1, I get 1. 1 times negative 1 is negative 1. And negative 1 plus 1 is 0. So the highest number I can get out is 0. Okay. Alright, so do the inverse now. So we'll switch the variable. And so we get x equals negative y squared plus 1. I like to put the negative 1 there instead. Let me just erase that real quick. Set the negative for the order of operations. Okay, so we'll add subtract step. Subtract 1, So x minus 1 equals negative 1y squared. Multiply, divide by negative 1. So y squared equals x plus 1, but that becomes negative. Exponent radical. So we'll square root that. But that's plus or minus since it's a even root, so we'll go over to here. We want to know the function of x. I am not getting that in today here. Let's try this. There we go. Equals, what did we get over here? We got the square root of negative x plus 1. Okay. Alright, so we need to know the domain. Well, the range should be the domain of the final one, right? Well, look, wait a minute here. If I think about this, negative x plus 1 must be greater than or equal to 0. So if I subtract 1, negative x is greater than or equal to negative 1. If I divide by negative 1, x is less than or equal to positive 1. So that's negative infinity to 1. Oh, wait a minute. That was a 0 over here on this one, so this should be a 1 or a 0. Let's take a look here. Well, if I plug in a 1 to the square root, I get the square root of negative 1 plus 1, which gives me 0. And if I plug in the infinity, negative, I get negative infinity plus 1, which is infinity plus 1, which is just infinity. Wait a minute. 0 to infinity is the range. Does that not match the domain over here? It does not. So this also needs to be restricted. Okay? So this function, which is an even, which is when the problem is, think back to the other page. If it's an even function, you have a problem. So that domain can only be 0 to infinity. You have to restrict it, because they must match. Let's look at the graph. We'll verify what we're saying is true. Okay, new graph. So the original we said was, oops, hit the wrong button there. Negative 1 times the x squared plus 1. Okay, parabola as we thought. And we said all evens have a problem. You need to start restricting domains at that point. So the inverse we said, let's see, menu, graph, function, and the square root of negative x plus 1. There we go. Okay. So we'll draw on here for a second. So clearly the inverse is this one right here, and it goes from positive 1 to negative infinity. Just keeps going off that direction, right? Okay. So therefore, these are not going to work for the original. You can't have both of these. Okay? It's not going to be the case. So remember, it's supposed to be symmetrical along this line, correct? Okay? So which one is the correct one? Well, it's going to be this one here, right? And that one is going to be 0 to infinity. Okay, because you can clearly see you can get to 0 there. Okay, so that verifies what we're saying, that so this is the domain of the original, and that is the domain of the inverse. Okay. Alright, let's go back and do the next two problems. Alright, so this is a cubic one. It's odd, so that should be less of a problem this time. So we have, this is the original. So domain, range. So I can cube positives, I can cube negatives, I can cube 0. So there is no restriction as to what I'm going to be. Okay, so if I plug this in, I get negative something to the third power plus 4. So if I plug in a negative infinity, 3 negatives is a negative, and a negative times negative is a positive. So essentially I just get infinity. If this is a positive infinity, 3 positives is a positive. That changes to a negative. Negative plus 4 is still a negative. So again, the output has no restriction. But this is a cubic. It should go in all directions. Okay, so let's do our inverse. Okay, so x equals negative 1 times y cubed plus 4. Switch the variables. Add subtract step. So x minus 4 equals negative 1y cubed. Multiply, divide. We'll divide by negative 1. So negative x plus 4 equals y cubed. Exponent radical, so we'll cube root. Cancels. So the inverse function is the cube root of negative x plus 4. So the domain here, I can cube root any positive or negative number, or 0. So the range here should match the domain here. So there is no restriction. We can prove that to ourselves with the graphing calculator. So let's look at it. So new graph. So the original was negative 1 times x to the third power plus 4. Then you graph another function. This was the cube root. What did we get? Negative x plus 4. So negative 1 times x plus 4. And we can clearly see, if I get the function out of the way here, that through the entirety of this, it lies along the y equals x, forever left, forever right, for domain for both. They are symmetrical, so everything is good. There's no restrictions on cubics or odds. Okay, let's try the last problem. This is an even root. So again, anytime there's an even root or even power, we're going to have restrictions and problems. So this is the original. So domain and range. So last time I checked, x plus 2 must be greater than or equal to 0 because it's an even root. Can't be negative. So minus 2, x is greater than or equal to negative 2. So I'm negative 2 or greater, which means I can be negative 2, but I can't get to infinity. Okay, so we'll plug those in to get the output, which is the range. So I get the y equals the square root of negative 2 plus 2, and y equals the square root of negative infinity plus 2. I'm sorry, positive infinity in this case. So that just gives me 0, and that gives me infinity. So I have 0 to infinity for the output. Okay, square root infinity, you get infinity. Okay, let's try the inverse now. Inverse. Switch the variables. X equals the square root of y plus 2. Add subtract step, there isn't one because the add subtract is inside the parentheses. Multiply divide, there just isn't one. Exponents are radicals, so I'll square both sides. So they'll cancel. X squared equals x plus 2. Grouping symbol will minus 2. X squared minus 2 equals y. Oops, we lost our y here. This is a y all the way down through, right? Okay. So f negative 1 of x equals x squared minus 2. Domain. Okay. So as I said, this is tricky because you look at it and you say, well, I can square any number I want, positive, negative, or 0. So there shouldn't be a restriction on my domain. But again, my range must match my domain, right? Because the range of the original is the domain of the final. The domain of the final is the range of the original. So I have to restrict this to 0 to infinity. Because if I was going to figure out the range, right, if let's say I plug in 0, I get negative 2. If I plug in infinity, what would I get? I would get infinity. Okay, so let's say I plugged in negative infinity. Would that make a difference? Well, negative infinity squared is still infinity, so I still get infinity. Okay, so it doesn't look like, okay, if I go negative infinity, I'm going to get what I want. So it doesn't matter whether I plug in a positive or negative number. I can't get to negative infinity. The lowest I can get to is negative 2, because 0 is the smallest thing I can get to. This part right here will never be negative. So as a result, 0 is the smallest it can be. So negative 2 will be my smallest value. So my smallest thing will be negative 2 to positive infinity, which matches the domain over here. But again, it doesn't ask for that. And all it asks for is what is the inverse and what's the domain restrictions, right? So that's the domain restriction for my original. That's the domain restriction for my final. So let's verify that graphically. So new graph. So the original was the square root of x plus 2. You can see it's negative 2 to infinity as we had specified. Menu, graph, function. And the new one is x squared minus 2. But as we said, there's a problem here. Okay? This does not match because it has to be symmetrical on the y equals x. Although you can square any number you want, we don't want the whole thing. So this part is not applicable. Since the domain here for the original is negative 2 to infinity, right? Starts at negative 2, goes to infinity. Then there has to be a restriction here of 0 to infinity. Okay, so the farthest left you can go with 0. So then you get your actual symmetrical parts. All right, that is the end of part 2.